Welcome to the Washington AI Network podcast. I'm Tammy Haddad, the founder of the Washington AI Network, where we bring together official Washington policymakers, DC insiders, and AI experts who are challenging, debating, and just trying to figure out the rules of the road for artificial intelligence. This AI revolution has been led by industry, and governments are running to catch up. There's no company more central to AI than NVIDIA. And today's guest is Rev Lebaredian, Vice President of Omniverse and Simulation Technology at NVIDIA, essentially the building of robot brains. He leads the product, engineering, and research teams of NVIDIA Omniverse. It's the software platform and operating system enabling developers to build physical AI and robotic system simulation applications. Earlier this year, NVIDIA unveiled smart robotics technology, and Rev is here to talk about the development of AI robots, where it stands out, and the timeline when it could impact so many elements of our daily lives and business. Rev, thank you for joining us. You've already thrilled audiences at the Special Competitive Studies Project Robotics Summit this morning. How are you going to build these robot brains? Let's just start right there.
Until recently, we actually didn't know how we were going to build these brains in such a way that they would actually be useful for us. For most of robotics history, the problem of how to build a brain for the robot remained unsolved. So we were building very specialized robots that were largely blind and largely not very smart. They just do the same thing over and over again. If you look at robots in industry, the most advanced ones are generally in the automotive industry inside their factories. You have these amazing robots. The mechanical nature of them is amazing. They can pick up whole cars and car chassis and move them around. But it takes a team of programmers weeks or months to program it to do that one action reliably over and over again. And the robot doesn't actually see or react to the environment. It's just screwing the same thing in the same place over and over again. If something goes wrong, it just goes wrong. With recent advancements in AI, and particularly generative AI, transformers, LLMs, we now have a line of sight to building good robot brains that are general purpose, so that we don't have to have a team of programmers program a robot to do the same thing over and over again. You can just have one human instruct the robot on what to do, and that robot will be able to see through all of its sensors and understand what it's seeing and create a plan to go execute on the task that you've given it. We no longer are going to specifically program them. Programming is just going to be talking in natural language or demonstrating to the robot what we want it to do, and it'll just do those things. So it's a race now to get there as quickly as possible. Our belief is that the fundamental science to do all of this stuff is already at a point where we have the basic bits of it. Now it's an engineering and systems integration problem. We have to bring together all of these technologies in order to unlock the next wave of AI, which is robotics.
Physical AI.
Yeah, physical AI in the physical world.
I have to ask, how did you end up at NVIDIA and get started on all this?
My background going way back is in computer graphics. I started programming when I was a little kid in the 80s. I was fortunate that my father bought me a computer when I was 6 years old.
Wait, where did you grow up?
Los Angeles.
Of course. Where else would you get a computer? Was it an Apple computer?
No, it was a Commodore VIC-20.
Commodore.
1981.
Do you still have it?
I don't have that one, unfortunately. I'd love to. Maybe my mom has it somewhere.
All right, talk to your mom.
I should go find it. But eventually that led me to computer graphics. I fell in love with the idea of computer graphics when I saw a picture inside a computer magazine that my brain couldn't make sense of. There were two balls floating over a checkerboard floor. It was obviously not a photograph, nor was it a painting. It was something in between. When I read the article, I understood that a computer program generated the image. And it did that by simulating the physics of light and matter and simulating what a camera would actually capture if you had a world like that. And I said, this is what I'm going to do, because I always wanted to draw. Half my family are naturally gifted in art, but I couldn't do that. But I could write programs. So I decided to learn about computer graphics. And then years later, I was just in the right place at the right time, living in Los Angeles, 1993, the same year that NVIDIA was founded. was also the same year the web was created, the World Wide Web. It's also the same year Jurassic Park came out.
One of the great movies of all time.
Well, for computer graphics, it was a seminal moment because for those of us that are old enough to have gone to the movie theater to go see that, everything changed as far as how we were going to make movies from then on. Once you saw those dinosaurs walking past you in the screen in their full glory, there's no going back to the old way of doing that kind of special effects, visual effects. And so all of a sudden there was a market for computer graphics. And I happened to be in Los Angeles where it was all happening. And I was 18 years old, so I could get a job. So I managed to wrangle a job at Warner Brothers that I would probably not have gotten if it was 5 years later. But they were so desperate for anybody that knew anything about this stuff that I managed to get that job. And then I went to Disney and worked on stuff that I would have no business working on, building systems to create hair and fur and render all of that stuff.
What was your favorite character that you created?
Well, I didn't create it. I created the technology that allowed others to do that. The software that I created was used in many films. That particular one was a big moment for me. When I was at Disney Dream Quest, I created a system to model fur and do the physics of the fur and then render the fur so that generate the actual images for a movie called Mighty Joe Young. The main character was a gorilla. And at the time, nobody had really done fur. This is 1996 when I started working on that. And we got nominated for an Academy Award for the visual effects for that, which was pretty cool. When I left Disney, I started my own company, developed some more software to do similar things, and I licensed it to all the big studios, including Disney. And it was used on many films, on Sum of All Fears, Stuart Little, X-Men, and so on and so forth back then, which eventually led me to NVIDIA. So it's the long route all the way there.
That is a real transition.
Yeah. So at the time, the kind of software I was writing was to do this really high quality visual effects for film. It takes a lot of computation to this day to create one frame of one of those movies. If you go to see a Pixar film or Planet of the Apes or something like that, each frame in terms of computing hours is many, many days worth of computing that has to be done just to produce that one frame.
And that hasn't changed with generative AI?
Wow. Oh, well, no, with generative AI, that's starting to change.
Okay.
But traditionally, this is what it takes to create a frame like that. But what NVIDIA was doing was creating special computers that could do the same thing, but do it in milliseconds instead of days. And by doing it in milliseconds, we could make the experience interactive. Instead of just watching a linear video of the thing, you could interact with it. And so that was really exciting to me. The hope that I would be able to immerse myself into these kinds of worlds, which are essentially video games, ones that look as real and as high fidelity and as physically accurate as what we were doing in film. So I worked on that essentially for the first 10, 15 years I've been at NVIDIA, taking the technologies we did largely for entertainment in linear, high fidelity film kind of context and applying it to the real-time interactive worlds of video games. But a little over a decade ago, when this whole machine learning, deep learning, AI thing was discovered on our computers, on our gaming computers, actually, when at the University of Toronto, Jeff Hinton, Ilya Sutskever, and Alex Krzyzewski discovered this thing, we realized that the way we're going to create the most advanced software and algorithms from then on had changed fundamentally.
You knew right away. You saw what they did and you knew right away.
Absolutely. We were waiting for it. We had put all of this computing capability into our gaming and consumer chips.
And you guys were the only ones, though, that did that. How did you know to do that?
It's Jensen, our CEO. He had the foresight, looking at the fundamental dynamics of computing and the markets, that basically every time we've seen more computing capabilities, more compute available for the same amount of money, same amount of energy, new applications were discovered. We find important things to do with this computing. And at the time, we had this thing called Moore's Law, which is not really a fundamental law. It was an observation that became kind of a self-fulfilling prophecy that every few years, the amount of computation available for the same amount of money, for the same dollar, or for the same amount of power was doubling or increasing exponentially. And we saw that it was slowing down. And so the computing architectures, the basic design of how a computer works had remained unchanged for decades because Moore's law was in effect. We could be kind of lazy and just write software once for the computers we have today and wait a few years, and it just gets faster without us doing anything. But with Moore's law ending, that was no longer going to be true. We weren't going to get these free speed ups. And if we lost those speed ups, if that curve slowed and stopped, that's actually a fundamental problem for all of society, because all technology innovation was dependent on that computing power increasing. It'd be a stop to innovation, essentially. So obviously that we can't abide by that. So we started designing a new kind of computer, what we call accelerated computers or accelerated computing, taking the processors and the type of computing we did for this one purpose, computer graphics and rendering, and generalizing it so you can use it for many other kinds of problems, like physics simulations and things that require really, really big computers. We put that capability into our install base, which was largely gaming computers, and waited many, many years till somebody figured out what to do with it. That happened at the University of Toronto with AlexNet, which started this whole big bang of AI. And we were waiting for it. We didn't know exactly what it was going to be. It turned out that the killer app wasn't an app at all. It was a whole new form of creating software and algorithms. And we understood the significance of that. This was a profound thing that had changed. So we set about going to work on accelerating the development of it by figuring out how to take our computers, which were largely in workstations or gaming PCs, and scaling it up so that we can have supercomputers that are what we are now referring to as AI factories. That's something we actually know how to do really well.
So AI factories basically have replaced data centers, right? Because everyone was talking about those. Are we the same thing?
They're replacing them. Data centers for the last few decades have largely been about collecting data and redistributing it. It's like for setting up our internet and maybe cataloging and databases and that sort of thing. AI factories serve a very different purpose. An AI factory is actually like a factory. Factories take inputs. You take material in as input, and out comes some kind of product. The inputs into an AI factory there's two inputs. There's power, the energy, electricity that comes in. The other input is data. It's information about the thing that's of interest. What comes out of it is intelligence. It's the first time we've been able to manufacture intelligence. And in order to do that, you need a lot of computing and a very specialized kind of computer. And that's the thing we set about designing over a decade ago. Now, the next question we asked ourselves when this new capability came about, the problem that team at the University of Toronto solved, image classification, has been a long-standing computer science problem since the beginning, since the 1950s. And most computer scientists had given up on the idea that we might have an algorithm like that would be as robust as AlexNet was and what we have today in our lifetimes. And so we asked ourselves, if we can now solve this problem, what are the other problems we should help solve? What class of problems can computers be applied to that would be of most value, that would make the most impact? And very quickly, if you ask that question, you go to, well, the problems we have out here in the physical world around us. Largely, we've applied computing to the things that are most easily digitized to ones and zeros. That's and language, text, the stuff that we have on the internet, that's the stuff that's just easiest to put in a computer. And so the AIs we've created so far are largely trained on that data, but they're constrained to the world of thought, to the human abstract thinking world. But our most valuable industries are actually outside in the physical world. They're the world of atoms around us.
Manufacturing.
Exactly. Manufacturing. So that's reassembling atoms. designing medicines and drugs, that's reassembling atoms into molecules that are useful for us. Transportation, moving people around, moving goods around in our supply chains. The world of information, IT, the technology world of information, is somewhere between $2 and $5 trillion a year, but everything else is over $100 trillion. And so how do we apply this amazing capability we have of intelligence, this new kind of software, this new form of computing to all of those markets? And so quickly we came to the conclusion it has to be robotics. That's going to be our bridge from the world of computing into the world of atoms, to manipulate things around us. To understand the world around us, you need robots that can perceive and do things out here. Well, how are we going to produce these AIs? Is then the next question. If the inputs to create an AI are energy, power, and data, well, where is that data going to come from to produce the intelligence necessary to understand the physical world and to manipulate the physical world? And that quickly led us to the conclusion that most of that data, most of that information is going to come from simulating the physical world. Before you can create a brain that operates on the physical world and understands it, you need to feed it with that data. And so we have to take the physical world around us and all of the laws of physics and what we understand about the world and represent it in a computer. We have to create a virtual world that matches that world as closely as possible and create simulations that match the laws of physics as closely as possible. So we could start moving at the speed of software in training these AIs that are going to be the components that are the brains of the robots we're going to put out in the real world.
Are you just trying to gather a lot of data with the simulators? Are you testing things out? In other words, do you have to spend another 3 years having your robots move around on the computer in order to have one that you can put in the real world?
No, we don't have to. We're already starting to put out robots in the real world. You know, we've been talking about self-driving cars now for over a decade, and they're actually here.
You call them robots?
They're robots. Robots are, in our definition, and I think in the general definition, it's any agent in the real world that can do 3 things. First, it can perceive the world around us. So through sensors and some mechanism, it gains an understanding of its environment and the things around it. Second, it can make decisions and plan on some actions it would like to do in response to what it's observed in the world. And third, actuation, acting upon the world. So
that's it. You're right. That's what cars do.
That's exactly what a self-driving car does, right? It observes the world around it. It understands where there's pedestrians, where there's street signs, and what state these street lamps and street signs are telling it, where the other cars are, and what they're doing. And then it makes decisions about how it's going to act to get to its goal. And eventually it actuates. It either brakes or accelerates or steers. That's a robot. Many things can be robots that we normally don't think of as robots. Buildings are becoming robots. They're robotic systems. Our headquarters building, we have sensors around the building that observe the world. Every day when I come into our reception area from the parking lot, there's a turnstile that has a camera sensor. That camera sensor detects that I'm walking up to it. It determines who I am. And based on whether I should have access to the secured area or not, it makes a decision. And then if it allows me to pass, which it usually does, it will actuate and some motors activate and the turnstile moves and lets me pass through. Then it watches me pass through to make sure I actually went through and updates a count of how many people we have in our secured area. And we use these same sensors and the same system to watch which areas of our building are most trafficked so that we could deploy our cleaning robots.
Is everything robotics there?
Not completely yet, but over time we're adding more and more.
Why do robots look like people? Why do you design or why are they designed that way?
Well, actually, mostly we haven't had human-looking robots for a while.
Elon Musk has them.
But now that's starting to happen. There's this wave of humanoid robotics that's coming. We're very bullish on that. At our big conference earlier this year, our GTC conference. Jensen, at the end, stood in front of a whole line of humanoid robots. Many, many companies are producing them, all for different specializations and use cases. The reason why we're seeing that and why humanoid robotics are important, you might think that, well, this is just kind of gimmicky. It's kind of a sci-fi thing. But really, if you think about it for a second, if we're going to build a general purpose robot that can do many different kinds of tasks and do it with us, assist actual humans, they're going to have to operate in spaces we've already built. And we've built those spaces for humans. Factories, warehouses, hospitals, office spaces, nurseries, kitchens, they're all designed around humans. They're designed around this form factor where we have 2 arms, 2 legs, eyes up here. We can reach things on shelves at certain range of heights, and so on. And so it makes sense that if we're going to retrofit existing spaces with general purpose agents that are going to help us, that probably the best form factor for them is going to be one that looks like humans. And so there's a race to go build them. The other advantage with humanoid robots is as we build the robot brains, we want to give them examples of the right way to behave inside the world around us. And we have lots of examples of humans doing things in these spaces. We don't have examples of 7-armed, wheeled robots, creatures running around for them to learn from. If we want to demonstrate something to a robot, tell it, this is how you should pick up this object and screw these things together, it's easier for us to demonstrate to a robot that actually is shaped and works like us than it is to something that's completely different.
What was your take on the Tesla humanoid robots that were recently revealed?
I thought it was remarkable. I mean, that's the first time we've seen that many humanoid robots intermingling with that many humans in this unscripted environment where anything could happen. Generally, we have to be very careful whenever we do these kinds of robotics demos because you don't know what's going to happen. There's a lot of things that could go wrong, so people are scared.
Oh, maybe some things have gone wrong. Do you want to tell us about anything unexpected?
So generally, they don't happen because people don't take the risks.
Right.
But the fact that we saw that means that the technology has actually gotten to the point where we're comfortable having these robots intermingle with the humans. They were making drinks and participating in this environment with all these humans. It's very remarkable. There's a lot of technology, both on the physical, the mechanical side of building the physical robot, as well as the robot brain. Just doing the low-level control to do something like pick up a glass and pour a drink into another glass without dropping the glass, without crushing it, it takes humans a while to learn that stuff. For those of us that have had children, it takes years before your baby eventually can do those things. And now they were doing it and we're almost taking it for granted. We're like, oh, that's
because of your earlier work in movies. See, you made everything look so real and easy. What is the biggest hurdle to building the robot brain?
We have a bootstrapping problem with building these brains. In order to create AIs, you need massive amounts of data. I think that's pretty well understood now. We've been talking about it in the context of LLMs for text and whatnot for a while. With the physical world, it's even harder. We need more data about the world with more diversity than even exists from all the photos and videos people have captured out there. And we need very specific kinds of data. In order to create this data, the only path we see to create enough of the data and do it in a safe and efficient way is to simulate these worlds and generate the data. In order to simulate those worlds, we have to actually create some virtual worlds that match the physical world as closely as possible. And the number of people that know how to create such physical worlds in the world is very small.
Yeah, where do you recruit?
Yeah, so it's either in Hollywood in visual effects or in video games. That's where all the experts are in this. But even if we have all of those people working 24/7 a day trying to produce worlds, we can't produce enough of those worlds. Fortunately, we can start using the AIs that we train inside these physical worlds, the same robot brains that were initially we're creating with these initial virtual worlds that were constructed by hand, we can use those same AIs to help us create more virtual worlds. The same skills you need to create things in the real world are the skills you need to create things in the virtual world, assuming that the virtual world is a close match to the physical world.
Well, that's the key, right? They have to match. But isn't that the hard part?
That's super hard. And that's what I've dedicated my life to. And that's what I'm still working on. There's a lot to do. And we've come really far, but there's a lot more to do. And it's one of these problems that's going to be an endless one, where we're always going to be getting better and better at simulating the real world, matching it with all its complexity and sophistication.
What about China? They just rolled out a large group of humanoid robots. Are they your biggest competition?
Well, I don't know if you're asking that question in the context of me as an American citizen.
I'm asking
or as NVIDIA.
I'm trying to get out whatever you'll tell me. First, as NVIDIA.
As NVIDIA, we actually don't feel that we're competing with anyone directly in this space, because we're not building everything about all of these robots. We don't build the mechanical robots. We don't build even the AI brains for the specialized applications. That's not our position in all of this. What NVIDIA does, and NVIDIA does well, is we build computers. We build the computing systems, and that's a special kind of computer that we call an accelerated computer. That's a combination of hardware, chips, systems design, as well as software that reaches all the way into the application layer of the stack. That's where our focus is. But by itself, none of the stuff we build is actually that useful. It's just core technology. It has to be integrated into other applications. We need other partners to go build the physical robots, to go build the robot brains, to build the systems to manage fleets of these robots and deploy them and service them and specialize them for all the different industries and different domains. We can't do that all ourselves. And so that's a problem that requires a large ecosystem, and that ecosystem is global. We have many, many partners around the world that are building these things. We're literally the only AI company that works with every other AI company. And that's because we've been very, very careful and deliberate about what we go work on. We go work on the things that nobody else is working on. We do it way before others even realize that this is something that should be worked on. Jensen famously calls these markets, these areas, $0 billion markets, $0 billion businesses. We like that they're zero because that means that there's nobody doing it. So we can go in there and be the first. And we have the tenacity to stick through it and invest in it for years, even over a decade in certain areas, until it actually becomes the thing.
You're a very brave man in AI. Do you feel brave to try these things out? And you could fail, right? It sounds like this is long, hard work on the edge of science.
That's true.
Sorry, I made you sigh.
Yeah.
That was a big sigh there.
I never thought of it as being brave. From my perspective, personally, I can't imagine working on anything else. There's so much to go discover, and the potential is so great for the technologies that we're creating. I don't know how to do anything else but be on the edge and the frontier, because it'd be too boring otherwise.
So we're in Washington, and it's an election coming up shortly, and there's always a party trick for debates, and that is the speed round. Okay, so here's the speed round. Sam Altman said at the UN General Assembly that superintelligence would be here in 1,000 days. What say you?
You know, I don't know what that means exactly. What people use these terms like superintelligence or AGI, the artificial general intelligence. It's really hard to even define what intelligence means. You know, this is the realm of philosophers and others to define it. From an engineering point of view, I think we can have some more concrete definitions that are practical. Intelligence is generally the things that is a main component of things that we build, systems that we build that do interesting things. And we can benchmark some of those things, those skills, against humans. In many respects, we already have super intelligence in specific areas that first AI that was born on our GPUs, AlexNet, it was an image classifier. It's an image classifier. When it first was introduced, it was still not as good as a human. It could tell the difference between a cat and a dog, but not as reliably as a human. Within a year or two, it was superhuman in its capabilities. It could tell the difference between specific breeds of dogs better than any human could. And we have this kind of intelligence, this kind of AI around us everywhere that's better than humans. The audio to text transcription, translation of text, we're starting to see they have superhuman capabilities in these specific kinds of areas. For the things that I'm working on in building, these robots, we already have some super intelligence that's very useful for those practical purposes. Whether we're going to have a kind of general intelligence that's superhuman in all aspects, I don't know. I don't know the answer to that. But I do know that for some very practical, useful things that we need right now to build these physical AIs so we can build robots that are going to help with all the demographic challenges that the world is facing, let alone the United States, we already have a lot of super intelligence that we can employ here.
All right. You're going to drive up to Capitol Hill or to the White House. You talk to our government officials. Is there a specific policy that you would like to push? I mean, there's a lot of talk about policy here. Obviously, we're the home of all policy. There's a lot of talk about how to prevent harms, whether you're talking about industry or individual. I know it's not your area, but is there anything you think about? You look at the U.S. government and you say, boy, I wish you would do this. Maybe it's to move you faster on robotics. This is not just about people. This is about science.
Yeah, it was great at the conference earlier. There was some discussion about this in the panel I was watching before we came here. I think it'd be wonderful if the government put together some grand challenges in the industrial space, like they did for the grand challenge for the self-driving cars. DARPA had that, was it 15 years ago or so? If we can put together a grand challenge of some sort for building a lights out factory that's fully automated, maybe not just a factory, but a network of them in a supply chain with digital twins of these factories that we use to optimize and operate those factories.
What are digital twins?
A digital twin, quite simply, is a representation of something that we have in the real world, the physical world, inside the computer, but with all of its aspects. So digital twin of a factory would be a digital version that's a simulation of how that factory operates. A digital twin of a car would be a digital representation of that car with all of its physics and all of its behavior modeled inside the computer. When you have these digital twins, you can then use them to do some amazing things, like test out potential future options. You could reconfigure your factory and try millions of different configurations and different speeds and feeds and see which one is the most energy efficient, which one is the safest, which one is the most productive, and go choose that in the real world to implement in the real world before going through all the time, expense, and material and energy waste building it.
That's actually a really good answer. John, you should march that up to Capitol Hill now. Lev, it's so good to meet you. I have 100 more questions, but I know you've got so many other people to talk to today. So I'm going to say thank you. Thank you for joining the Washington AI Network podcast. We're honored to have you in DC, and take me to one of your AI factories.
Well, they're actually not our AI factories. We produce all of the essentially the equipment that goes into these AI factories, but we'd be happy to arrange for you to see one of them. You should come visit us at our headquarters, though. We have a lot of other cool things to show you there.
Oh, I'd love to come to your headquarters. One of the things I love about NVIDIA is you guys are so smart because you come up with all this technology. And then you say, okay, Amazon, Microsoft, okay, all you guys figure out the rest of it. Genius job there.
Well, we also help them as well.
I know you do. You don't leave them behind.
Yeah, we want to carry everybody along with us.
Well, you created this ecosystem, not just from the scientific point of view, but just the way you talk and Jensen talks about bringing everyone together. It's a real gift. Thank you.
It's a real pleasure being here. Thank you so much for having me.
Come back to DC.
Anytime.
Thank you. Thank you so much, Rev Lebaredian, Vice President of Omniverse and Simulation Technology at NVIDIA. We're so glad to have you here. This is the Washington AI Network podcast. Please subscribe and follow us on Instagram and all the other social platforms. Thank you for being with us. Thank you for listening to the Washington AI Network podcast. Be sure to subscribe and join the conversation. The Washington AI Network is a bipartisan forum bringing together the top leaders and industry experts to discuss the biggest opportunities and the greatest challenges around AI. The Washington AI Network podcast is produced and recorded by Haddad Media. Thanks for listening.